Assalamu alaikum, dear students. Today we are going to discuss the grain size analysis of soils. Today is lecture number 12, week 6 of Geotechnical Engineering 1. So let's begin today's lecture. Grain size analysis or mechanical analysis. Why we do that? Because if you take a soil in your hand or you observe generally outside, if you look at any soil, you will observe that it is rarely consisting of a single size grains. It will have all the different sizes of grains. There will be larger particles, and then there will be smaller than that, and then there will be further smaller particle than that. So the purpose of grain size analysis or mechanical analysis, or in some books it is written as particle size distribution as well, is determination of the size and range of the particle present in a particular soil. That is usually expressed as a percentage of total dry unit weight. So you basically determine the sizes of the particles in this and the percentage of each size. For example, we can determine that how much percentage of the soil is consisting of 2 millimeter particles or 4.75 millimeter particles, okay, or less than that or greater than that. So we know that in soils you have got, as I discussed, larger particles and then smaller particles as well. To distinguish between large or coarse grain particles and small or fine grain particles, we have drawn a line at 75 micron or 0.075 millimeter. So 75 micron is 75 parts out of 1 million of 1 meter, alright, or 0.075 millimeter or 75 micrometer. So this is very small, okay. You can imagine taking 0.075 of 1 millimeter. So the particles which are smaller than this are classified as fine grain, which we will be later on discussing as silts and clays. And the particles which are greater than 0.075 millimeter in size are classified as coarse grains particles, and that includes sands and gravels, okay. So then we further distinguish them into a different, that gravels are greater than 4.75 millimeter and smaller than 4.75 and greater than 0.075 are sands, and then silts and then clays as well. So this mechanical analysis or grain size analysis provides us that how much percentage is coarse grain or fine grain, and then in coarse grain how much percentage is 2 mm, how much percentage is 4.75 mm, how much is 8 mm, different size of the particles present. The purpose is to let you know the composition of the soil and also the distribution of the particle sizes. Obviously, if the soil consists of a large particles, this can be designated as a strong soil, but the fine grains are also important because of the presence of the fine grains, the soil will be in the densest state. Because if the fine grains are not present in this material, which I am showing over here, then these will be empty pores, and you know, if there are empty pores, that can result in reduction of the dry density, and also that can later on result into the settlement of the soil as well, or being compacted. So that's why to get a soil in a most compacted form, we usually require all the different size of the particles in particular soil sample, which is known as well graded soil, or in some books known as graded soil as well. We will have a detailed discussion later on about well graded and gap graded and uniformly graded soils in the coming lectures. So there are two methods which are used for grain size analysis or mechanical analysis. Firstly, sieve analysis. In sieve analysis, we use different sieves, which you can see over here. There are various sieves which you may have seen. You sometimes use them in your household to sieve the floor as well. So they have different openings and they are stacked together like this, and in the bottom there is a pan which does not have the option to allow the particles to pass, while in the rest there are sieves, there are openings which have specific calibrated size, so they can allow certain particle size to retain on that, and the smaller particles are allowed to pass through that sieve. So here you can see some of the representative soils. Obviously these soils are very fine, so they will not be retained on this sieve and they will just simply pass through it, and they will be only retained on the sieve from which their size is greater. So that's how we will know that how much percentage of a particular size is present in a particular soil sample. So this is usually used for a particle sizes greater than 0.0075 millimeter, because this is the smallest sieve which we use. We call this sieve number 200. So this is what we used for the smallest. We use this. The largest for the gravel we use 80 mm sieve, which I will discuss in a while. So because the particles which are smaller than 0.075, they are difficult to be sieved because the sieve size becomes so smaller. So for the fraction of the soil which passes through sieve number 200, we will use hydrometer analysis, or also known as sedimentation analysis as well. This fraction, which is usually passing through 0.075 millimeter, includes silts and clays, while the fraction which is retained above 0.075, so it means that its size will be greater than 0.075, will be sands and gravels. So sieve analysis is used for the particle size distribution of sands and gravels, while hydrometer analysis is used for the particle size distribution of silts and clays in a particular soil. And usually we perform both tests and plot them on a same graph, which is known as combined gradation curve. We will discuss that in a while, but over here you can see the Sieves analysis setup, and on the right you can see hydrometer analysis setup, in which we disperse the soil in a water solution and then dip this hydrometer in this solution, and according to Stokes' law the particles settle and they sediment, so the specific gravity of the soil changes, and that indicates the particle sizes indirectly. So this is usually used for the smaller particle sizes, as I discussed over here. So the equipment setup is given on the right for the hydrometer analysis and on the left for sieve analysis. Moving on, what type of sieves are available? In this table, US standard size according to ASTM are provided. You can see the sieve number and the opening of this particular sieve. For example, first sieve mentioned over here, these are the, by the way, sieves for the soil particle size analysis, not for the aggregate or gravel. I will discuss that in a while. So the largest sieve is sieve number 4 with the opening size of 4.75 millimeter. So for example, if this sieve is sieve number 4, number 4 means that per linear inch this sieve has 4 holes. So if you count the number of holes in 1 linear inch, they will be 4. So that basically refers to the sieve number. So if this distance is 1 inch, okay, then there are 4 holes in this 1 inch, okay, sorry, to here, 1 2 3 4. So 4 holes per linear inch will basically means that this sieve is sieve number 4. Remember, this is the number of holes per linear inch, not per square inch. Alright, sometimes students mix it with the number of holes being per square inch. This is not per square inch. Similarly, sieve number 5, it means it will have more holes per inch. So if in 1 inch there are 5 holes, the size will be obviously smaller. So the opening size in sieve number 5 will be smaller than number 4, and it is 4 mm. Then sieve number 6, it will have 6 holes per linear inch, so more holes in 1 inch length, so the size is 3.35. and sieve number 7, 8, 10, 12, 14, and so on, and we use up to sieve number 200 usually in geotechnical analysis. Okay, so our starting sieve is number 4 and our ending sieve is sieve number 200. So we usually determine the size of the sieve to be used according to the size of the soil which is being analyzed. So as I discussed, the sieves are selected. The standard sieves commonly used for the test are provided in the following. So if you take a soil which has got both gravel and sand component, remember the smallest size is 75 micron, so it will be above that, so this limit will be 75 micron or 0.075 millimeter. So for the particle size between 0.075 millimeter and 4.75 millimeter will be known as sand, and for that we will use the sieve set for the sand fraction. And then the particle size which is above 4.75 mm but less than 80 mm, for that we will use the sieve set used for the gravel portion, and that will be sieve set for the gravel. So sieve set for the gravel will consist of 80 mm sieve, which means that the opening size is 80 millimeter. Remember that 1 inch is equal to 25.4 millimeter. So this is approximately slightly larger than 3 inches opening. So the opening will be slightly larger than 3 inches, so you can visualize how much it will be. It will be roughly on this from here up to here. Okay, so quite a larger size particle. And then you have sieve number 40, which 40 mm sieve, which has opening size of 40 millimeter. Then 20 millimeter sieve, which has got opening size of 20 millimeter, 10 millimeter, and the smallest sieve used for the gravel is 4.75 millimeter, as we know that the gravel size is greater than 4.75. So any material which will pass through this sieve will have size less than 4.75 millimeter, so it will not be gravel. So we'll just collect it and put it in this set. Now any material which is passing through 4.75 millimeter will be either sand, silt or clay. So we will put it on this sieve set, and over here the sieve set for the sand consists of 2 millimeter sieve, which has got opening size of 2 millimeter to start with, then 1 millimeter sieve, 600 micron sieve. Okay, its size is 600 micrometer. So, or you can divide this by 1000 and that will be 0.6 millimeter. You can get it in millimeter as well. And then you have 425 micron sieve or 0.425 millimeter sieve, 212 micron sieve or 0.212 millimeter sieve, 150 micron sieve or 0.15 micron sieve, and 75 micron sieve or 0.075 micron millimeter size sieve. So any material which passes through this sieve will be considered as silt or a clay, and for further particle size distribution for this side which is passing through this sieve, we will be using the hydrometer analysis, while the fraction of the soils which are retained on these sieves will be known as gravels, and the fraction of the soil which are retained on these sieves will be known as sand. Now, the procedure. What type of procedures are used? You will be conducting this test in the laboratory. So the detailed procedure will be discussed in the lab. Over here, we are just discussing what types of tests are available and what type of calculations is to be done and how the graph or the plot will be plotted for the sieve analysis. So there are two techniques to which we do the sieve analysis, which includes the wet sieving and the dry sieve. Now, if your material is clean sands and gravels, then you can use the dry sieving technique. What are the clean sands and gravels? The clean sands and gravels are sands and gravel which does not have any clay or silt fraction in it. Usually you find them in the river beds, nallas, etc., where the sand is very coarse and clean, which you usually use for the plastering of building. You consider that to be a good sand. And also in case of gravels, they are like aggregate pieces with no clay or fine soil in between them. But if there is a fine soil there, then it will cling to the aggregate. Okay? It will stick to the surface of the aggregates. So when you are sieving those soils, they will, although they are smaller in size, but because they are attached to this particle, they will not go through the sieve. So they will be retained on this sieve, and it means that their size is greater than this sieve, which is obviously not. So if we have 5 to 10% of the clay or greater than that in a given soil sample, clay soil, if we have gravel and 10% clay in this, so in that case we will not be doing the dry sieving technique, but we will be using wet sieving technique, in which we will put the material on sieve number 200 and then we will put the pan behind it and then we will wash it. And we will take this brush and make sure that all the lumps of clay or silt which are attached to these gravels are washed down to this pan. So then we will oven dry this sieve. We will take this weight, and this will be the sand or gravel portion which we will do in the using dry sieving technique, and the one which is passed through this, that will be obviously clay portion or silt portion, and that we will be using hydrometer analysis to analyze that portion. Okay, so that's why if your soil contains clay, even a trace amount of 5 to 10%, you will be using wet sieve. Many times people use dry sieving technique for clay as well, and they oven dry it and then pulverize it with hammer, which is not recommended, and it is not ASTM standard procedure, because through hammer you cannot detach the particles, the small particles which are attached to the surface of sands or gravels. For that we need to wash them away. So we will discuss in detail about wet seeing and dry seeing, and we'll perform them in the laboratory, so you'll understand them further. So the smallest sieves we'll use over here in the mechanical analysis. In the sieve analysis will be sieve number 200. The portion retained on each sieve will be collected separately, oven dried before the mass retained on each sieve is measured. So when we do the sieve analysis, the portion retained on each sieve, they will be placed in oven for drying at 110 degrees centigrade for 24 hours, and then after that their weight will be measured, and that will be the weight of the dry soil retained on that particular sieve. Over here, by the way, sieve number 200 is shown, which you can see over here, very small opening size. So moving on to the calculations. What type of calculation you will be doing? So once you have placed the soil in this sieve sets, we place them on sieve shaker and shake it for 10 minutes. After 10 minutes, then we take out all the sieves, and you will see there will be mass of the soil retained on each sieve. Okay, the largest opening size sieve will be on the top, and the smallest opening size sieve will be at the bottom. So the larger particles will be retained on these sieves, and smaller particles will be retained on the bottom sieves. So what we will do, we will put them, as I mentioned, in the oven for drying at 110 degrees centigrade for 24 hours, and then once we take them out, we will determine the mass of the soil retained on each sieve. Okay, so for example, M1 will be mass on this, M2 will be mass on sieve number 3, and M3 will be on sieve number 3, and M4 will be sieve number 4, and similarly Mn will be sieve number last. So, and MP will be in the pan. So now what we will do, we will determine the total mass by adding all the masses retained on all the sieves. So from M1 to M2 to Mi to Mn plus Mp, which is the pan. Okay, so we will determine the total weight of all these soils retained on different sieves. We will add all the weights on all the sieves, and that will be the total weight, and we will determine that. Alright, after that we want to determine the cumulative mass retained. What is cumulative mass retained? For example, if I want to take out this sieve and want to determine what is the cumulative mass retained, the cumulative mass retained will be the sum of mass retained on this sieve plus the mass retained on all the sieves above them. Okay, so all these mass added together, that will be the cumulative mass retained. So if this is like sieve number I, so M1 plus M2 plus M3 plus Mi, or M4 in this case. So M1 plus M2 plus M3 plus M4, if I add them together, that will be the cumulative mass retained on this fourth number sieve. Okay, so that will be the cumulative. This is all the mass, all the particle sizes which are greater than this opening of this sieve. So that will be the cumulative mass retained, and we want to determine that how much mass has passed through this sieve, which is known as percent finer, and that will be used. So for that we need to subtract the cumulative mass retained, which is this one, okay, from the total mass. Okay, so total mass minus the mass retained, cumulative mass retained, will give you the cumulative mass passing. So in that manner we can basically determine the percent finer, which will be the mass passing, which will be the total mass minus cumulative mass retained on a particular sieve, like sieve number I. So fraction which is passing through or finers from sieve number I, which in case, like for example here I am saying sieve number 4, so it will be F4 will be equal to summation of all the masses minus M1 plus M2 plus M3 plus M4 divided by total mass, multiply by 100. That will give you the percent finer, which means that that much percentage material is finer than this sieve. So if it is finer in size than this sieve, so it will pass through it. Okay. So in this fashion, we will determine the percent finer for each sieve opening, for 4.75, for 4 mm, for 3 mm, for 2 mm, 1 mm, all the way up to 0.075 mm. And we will plot it in a table and then plot them on a graph showing the sieve opening size in millimeter on the horizontal axis or x-axis or abscissa, and the percentage finer on the ordinate or y-axis. So this graph basically shows that a particular size of material, how much percentage is present. For example, 1 mm is shown at this over here, so which is 1 mm particle sizes. So if I plot this on this scale over here, sorry, it's not very ideal. So it means that around almost 88 or 89% material is larger than 1 millimeter in this. Okay, and almost, like you can say also that 83% material or 88% material is smaller than 1 millimeter in this. So over here you can see 4.75 up to this is gravel, this is 4.75, okay, and then 4.75 to 0.075, which is this line represented, is sand, and this fraction will be determined later on using hydrometer analysis. So in sieve analysis, we are only discussing right now determination of this portion of a graph, which is also known as S-curve. Now, it is also worth mentioning that this is plotted on the semi-logarithmic scale. So this is log and this is normal scale. Why semi-logarithmic scale? Because semi-logarithmic scale allows you to plot the largest sizes and the smallest sizes to the same ratio, same width on a graph. If you are plotting them on a normal graph, then these fractions will become so small that they will be plotted above each other, and they will become so small that you will not be able to see them. So log basically have different ranges, you can see, for different sizes, and they are of equal width. Okay, you can see over here. So that's why log scale is very important. So this portion on the right of this line will be plotted using sieve analysis. This portion will be plotted using the hydrometer analysis or sedimentation analysis, and when we plot it combinedly, this is known as combined gradation curve. So what it tells you? It basically tells you that your soil mass in the given soil has this much size ranges, alright, which is 0.0003 to up to 80 millimeter in sizes, or 70 millimeter, I guess, in this case. So, and their percentage is given in the following. Like if you want to see that how much material up to 50%, like how much material is 50% over here, how much size is smaller than 50%. So you can come here and see, if I drop the line over here, this is 0.1, 0.2, 0.03, yes, 0.03. So it means that 50% of the material is smaller than 0.03 millimeter in this soil sample. So this can be considered as fine grained soil as well. Over here you can see majority of the soil is silt or clay. Okay, silt starts from here, so you can see over here up to 65% material is either silt or clay, while the remaining 35% material is sands or gravel. So this information will be used later on for classification of soil, which is our purpose why we are studying this. We will also study another topic for that, which is Iqbal limits or plasticity liquid limit later on, shrinkage limit as well, and we'll be using this information later on to classify the soils into various groups. So in next lecture we will discuss the hydrometer or sedimentation analysis. If you have any question regarding this lecture, you can ask on the portal or in the Zoom meeting. Thank you very much for listening.